תל אביב 360, ערוץ הפודקאסטים של אוניברסיטת תל אביב.
Hello to everybody, all our audiences in Israel and around the world. This is a series called It's All About Chemistry, and this is one of the episodes here on the Tel Aviv University podcast channel. My name is Gili Remen, and I will be your host for today. I'm a graduate student at the Lowy International School here at Tel Aviv University, studying cyber politics and government. And professionally, I'm a journalist with 5 years of experience producing news shows at CNN in New York. Today's podcast, I'm thrilled to introduce our guest for today, Professor Roey Amir from Tel Aviv University, who's revolutionizing how drugs and agricultural treatments reach their targets. A little bit about Roey. First, his background. After earning his PhD at Tel Aviv University, where he developed self-immolative dendrimers, Professor Amir continued his pioneering work at UC Santa Barbara, focusing on enzyme-triggered self-assembly polymers. Since 2012, he's led research at Tel Aviv University, designing smart delivery systems that can respond to their environment. His breakthrough work spans both medicine and agriculture. He heads the medicinal chemistry unit at the Blavatnik Center for Drug Discovery and leads the Adama Center for Novel Delivery Systems in crop protection, developing innovative solutions for targeted drug delivery and sustainable pest management. Today we'll explore how his smart molecular systems could transform treatment of diseases and protection of crops. Welcome, Professor Amir.
Thank you very much, Gili. Nice to be here.
Good to have you. For our listeners who may not have a strong chemistry background, could you explain what polymeric micelles are and why they're important for the drug delivery system in your research?
Yes, of course. So even for everyone that thinks they're not an expert, they actually are an expert, because every time you wash your hands with soap, this is what you make. You make micelles. They're not essentially polymeric. So polymers are a bit longer or larger molecules that have one side that is hydrophilic, that likes water, and the other side that is hydrophobic and it hates or fear from water. And so when you put, for example, if you try to wash your hands after touching some oily residues without soap, then it doesn't come off your hands because it sticks. It's not soluble in water. But if you use these amphiphilic structures, they form this type of basically what looks like a small nano balls. Okay, that the inside is hydrophobic, and this can encapsulate or hold inside the hydrophobic residues, so oily residues. And this is basically what allows us to wash hands. Now, what we try to do in the lab is to make these spherical structures, these balls, and use them as a nano-carrier. It means that we need them both to hold hydrophobic cargo inside, that this can be a drug or an active ingredient for such as a pesticide. But we also want to design some mechanism that would allow them to be released.
Right.
Okay, because if you want to kind of help medicine or agriculture, you need to both encapsulate it, allow it to kind of get to its target site, and then being able to release there so it can do its active role.
Right. And that was kind of my next question. In your research, you often talk about creating a smart drug delivery system. What makes these systems smart, and how do they know where to release their cargo? For example, if you're developing a drug that is targeting, let's say, the thyroid, how do you design a drug that is inactive in the body but activates only when it gets to the thyroid or to the place that it needs to go?
So I would say in general there's two different approaches for that. One is to actually modify the drug itself. Okay, and this is very often called a prodrug. So you take the drug, you modify it with something, some chemical moiety that makes the drugs inactive. And then when it reaches the target, there should be something in the target site that can break this thing that you put on, and then the drug goes back to its natural structure and regains its activity. This is extremely, so there's a lot of researchers working in this direction, and I have some work in the past in this direction too, but mostly from my PhD. But in my independent group, we kind of moved into another approach, which is also used by many different groups around the world. And this is to make a carrier that would allow us to do this change. So the idea is that the carrier would hold the drug or the active ingredient inside and be very stable, so allowing it to be injected into the body, go into the bloodstream, travel everywhere around, but being not active and hold the drug inside. So basically it's a benign kind of thing that goes inside.
Yeah.
But only when it gets to the target site, which we have to pre-design. So we need to know and talk a lot to our, friends in biology in the School of Medicine or the School of Plant Science, again, depending on the application,
right,
to kind of understand better what different conditions are there in the site of in the target site compared to, let's say, normal healthy sites where you don't want to release
of course
active ingredient. And then, so very often we call them smart carriers, even though, again, when I give talks to high school or kids at school, these carriers are not as smart as these kids, right? If you ask them a general question, kind of...
They won't know the answer, yeah.
Yes. So I would say it's more of a smart design, to design them in a way that when they encounter something that is different in the environment, they would sense it and fall apart or transform into something else that would allow you to release the drug. So most of our work is focused on enzymatic stimuli. So enzymes are basically the machines of the body or of nature. So almost any process in a living system is occurring by enzymes. And we try to design our carrier to respond to these specific enzymes. So only when they see them, sense these specific enzymes.
Yes, that's actually my next question. Your recent work, you said, focuses on these enzyme receptive mast cells. Could you explain how the enzymes can act as triggers for the drug release and why this approach might be promising? So
I'll start with the end.
Yeah.
So as I said, enzymes are the machines of nature, and almost every action or something that happens in a living system is occurring by enzyme or catalyzed by enzymes. And when we are sick, or then it doesn't matter if it's if it's cancer or COVID or anything, there's a change in the enzymatic activity because. Again, when you're sick and your body is kind of out of balance, it also goes into the kind of molecular biological level when there's a out of balance activity of the enzyme. So some enzymes would be, their activity would be reduced and some would be enhanced. And so if we can know which enzymes are overexpressed in these specific diseases, then we need to kind of go to the drawing board and draw, a chemical structure that would be able to respond to this enzyme, and this enzyme can either completely degrade the chemical structure or change it in a way that would eventually allow eventually the carrier to fall apart and release what it carries inside. Now, so this is kind of the end why this is so attractive, because the disease is already overexpressing these enzymes,
in the
then
body.
Triggering them or focusing on them. This should be the holy grail of this field. On the other hand, what makes it so difficult is that this enzyme were not designed, by evolution to act on our polymer carriers. So we have to fit and play it, and there's a very kind of a balanced, dedicated, dance between a stability of a carrier and its ability to respond to an enzyme.
Why is the outer layer of the carrier matters so much for the drug delivery performance?
Because eventually this is what the environment see, right? So let's think on something that is completely different than what we usually consider as molecular sciences.
Yeah.
Okay, so an airplane or a boat, right? It can carry different cargoes inside.
Right.
But what affects how fast it can fly or sail is what touches the water or the air, right? So it's a kind of a dynamic kind of a signature and an ability to go through waves or go through water. So very similarly, the shell of the carrier is what is in charge of interacting with the environment, or interacting or allowing it not to interact with them.
Right, staying inactive. Yeah. Interesting. In your research, correct me if I'm wrong, you created tiny carriers that can change from floating particles to gel and then dissolve completely. It's almost like ice changing to water and then to vapor. Why is this shape-shifting ability useful for delivering medicine? So
first I want to say that this was it's very often happening in science, completely by serendipity. So this was not what we were planning to do, okay? We're trying to make some control molecule and study how it behaves. And then the student that was working on it came one day and she said, there's mast cells that we have that are in the area of 20 nanometer types of spherical balls.
It's tiny.
That they are basically disappearing from the vial that she was testing. And I was like, they're not supposed to. Okay, and we were puzzled, and we were scratching our head and trying to figure what's going on. And then we actually opened the instrument that we used to analyze them, and we saw that we had some hydrogel precipitating at the bottom of the vial. And then makes us to understand that we achieved something that, again, in the beginning, this was not our plan.
Right.
But we understood that we achieved, indeed, this ability to start with a micelle. So, again, a very small 20, 30 nanometer size of a spherical ball that can penetrate nearly, through tissues and definitely blood vessels, and it's a very tiny thing that can travel around. But then think that, and previously we were kind of working on using this carrier to potentially hold the anti-cancer drug inside, let's say, and this would be able to travel, meet the cancer enzymes, and then being activated. But this means that also that the drug that would be released very fast, right? Whenever it meets the enzyme.
Right.
Now, if you have a system that can do this mesophase transformation, so going from a 20 nanometer size micelles into hydrogel particles that would actually aggregate in the site of disease, this means that we can start from a micelle and then generate something that would serve as a drug depot in the site of disease. So now you can start dreaming about, giving this. Again, it's not going to happen, not today and not tomorrow, okay? But potentially giving this to a patient and allowing the drug to be released for weeks, maybe a month, maybe a year.
Right.
Okay, so you can generate inside the body a drug depot that would be releasing drug very slowly. So this means that you don't have to bring, the drug, the patient to the clinic every few days a week.
That's amazing. I'm curious. You said that they're literally nanoparticles. They're so small. What kind of instruments are you using in the laboratory to test this, and how are you seeing this to the naked eye?
So you can't see them with the naked eye, not even when I was younger and had a better sight. We use different types of microscopy, from transmittance electron microscopy and scanning electron microscopies. So different types of microscopy that allow you to look at things in this size range.
Right.
We also use different types of light scattering. So an instrument such as dynamic light scattering, an instrument basically shines a ray of laser light through a sample. And I'm sure that you know that sometimes you sit in a dark room and you have this ray of sun that comes through the window, and then you can see different particles in it.
Yes, in the actual air,
Yes, and then if you turn off the light, they disappear.
You don't, right.
So this is basically the scattering. So we have an instrument that does this in a bit more controlled way and can then tell you what is the size of the particles that were in this ray of light that goes
Interesting. You mentioned different medicines potentially for cancer treatments, and I was kind of wondering, chemotherapy is known for its harsh side effects because it attacks both the cancer cells and the healthy cells. How might your research help reduce these side effects specifically for cancer patients?
So this is exactly the thing, that most cancer drugs are designed to interact or to affect any cell that is dividing very rapidly or uncontrollably.
Yeah.
And so this goes obviously to the cancer cells, but not only, as you said. So it affects also the immune system. It affects the guts. It affects the hair.
Right.
So it affects different levels in the body that really limit eventually the ability of a physician to kind of balance between killing the cancer and killing the patients.
Yeah.
And I can tell you actually from my own personal experience of someone who died very recently from that was very close to me and died out of a very aggressive cancer, is that at the end of his kind of his last days was really in a very severe kind of situation due to loss of a bone mass. And this is all from combination of chemotherapy and even more advanced kind of biological therapy, so antibodies. Right. But still, they require you to take down the immune system so you can allow this action to happen. So again, let's stay very naively and optimistic. So let's think on our micelles being injected, being completely, again, benign to anything.
Right.
Traveling in the body, reaching the tumor, being activated there by an enzyme that is overexpressed only in the tumor. Mm-hmm. Or by a few orders of magnitude more than in the tumor than in other places.
Right.
Accumulate there. So they start changing from micelles into these hydrogel aggregates. Mm-hmm. Stay there. Then slowly start to release a drug only in the site of disease. Mm-hmm. So everywhere else from the body, they already would be cleared.
Yeah.
And then you create this site of drug that is being slowly released only in the site of disease. And the drug would be slowly released there. And eventually, when all the drug is released, our carriers are also designed to kind of self-eliminate later.
And dissolve.
So they would completely go further degradation, go into hydrophilic polymers, and then being able to be excreted from the body.
That's amazing. Beyond cancer, what everyday conditions might benefit from this smart delivery approach? Could this help people with diabetes, arthritis, or any other common diseases? And are these medical innovations and products close to being available to the market, or is it still kind of far away?
So beside cancer, which is actually a family, right, of different, because we have
many different types of cancer,
and each one of them is different. We can think on a kind of a bacterial infection that this can be relevant, so some viral infections. Mm-hmm. So whenever you have, and I guess it holds for many different types of diseases, that you have a different situation, right? This is what we kind of harness to activate. We need different conditions in the site of target compared to other areas.
Right.
If there's a difference, then we should be able to tailor something that would react to this difference. Mm-hmm. It's not an easy process. Not everything that we do is successful. Sometimes we manage to make more successful things than what we plan to do, as I described before.
Yes.
And now, when are we going to see something like this coming to the market? This is a bit hard to tell. I would say that most of my research in the group is very focused on understanding the fundamental aspect of this.
Yeah.
So how can an enzyme that is commonly 5 to 10 nanometer in size can interact with such a micelle? What are the kind of structural parameters of the micelle and the polymers that make it, that govern this interaction with the enzyme? Where does the interaction happen in the surface, or the polymers have to come a bit out? So there's a lot of very basic science questions that need to be addressed.
Yeah.
I have still roughly, I would say, 20 years before my pension. I hope to be able to bring it. Yes.
Yeah, there's a lot of time. Let's shift to agriculture. Many of us worry about pesticides washing away in rain or affecting beneficial insects. How could your smart packaging approach help create better, more targeted crop protection?
So from my kind of the way I see it, from the eyes of an organic chemist, or I would say it's the same, right? Just like the body, we want to affect only the site of disease in the body, and we don't want to affect other areas. So I would say it's potentially the same. Mm-hmm. So we want to target only the bad plants, or only site of disease in plants. Mm-hmm. I would say the most significant difference is, this is only even when just discussing, with my colleagues and in the school of, let's say in the School of Medicine, when we plan some checking anti-cancer activity of some of our carrier, or talking to my friends in plant sciences or agriculture company, there's a very big difference in the amount of material that you need, right? For to inject something to a mice to be tested, you need like a very, very small amount.
Yeah.
To make, to spray a field now, or even few plants, then you need, a big bottle of. Mm-hmm. So you need to make sure that your chemistry is very robust, that is scalable, that you can make, everything on a much, much larger scale. The price should be much, much higher, right? So some drugs, treatments today can cost, $10,000 and more of dollars. No one would, at least now, would spray their plant with for a $10,000 type of formulation. So this is, again, something that on the science side, you don't think about it. Mm-hmm. But when you talk to an agriculture company, you go like, do you want to try to test my technology? And you go like, how much it costs?
Right.
So this
has to be more practical.
Yes.
And are you working directly right now with agricultural companies or with medical companies to develop specific drugs or specific pesticides for them?
So we work with. So first on my personal level, we had some project with Adama, which is a very big agriculture company here in Israel, and I had some projects trying to basically test the technologies that we develop in my group and try to see if we can implement them towards agriculture. And then kind of a few years later, it kind of evolved into establishing a center here in the university that has been mostly focused on the education of students in this area of basically formulations for agrochemicals. We actually have a couple of courses, theoretical courses, including a practical course. One is actually starting right now.
Oh, wow. So it's designed specifically
towards agriculture. Yes, for agrochem. And we have a very tight collaboration with Adama. So actually my lab instructors are not PhD students, as they usually are, but they are actually team leaders from Adama who are guiding our graduate students in how to prepare an agrochemical formulation, test it, and evaluate it. So for the first time in their life, the students that are taking the course would spray at the end of the course, so sometime in June, they would spray plants, and if the plants would die, then they would get a high grade because they're trying to develop something.
Right. That's so funny. If you applied your technology to agriculture, could it mean farmers would need to spray their fields less often? How would it work? What specific challenges exist in developing delivery systems for agriculture that might not be present in the medical world, let's say?
So definitely, yes, spray less and less often. Ideally, again, if something can adhere to the leaves better. Right. Or and then again, and spray less because it potentially would go into a target site. Again, we already discussed the question of scalability of different scales. Right. But there's another thing that in a way is way more challenging in agriculture than in another medicine, even though medicine seems to be we think that it's much closer to our hearts, even though, again, if you think on,
bigger scale.
Yes, hunger, then...
Right. People it's still a life or death.
Yes.
It's still a life or death. Medicine and agriculture is both life and death. Yeah.
Yes, but I would say most people think that medicine is ranked very high and agriculture is way below, even though, again, if there's hunger and no food, who cares about medications, right?
Right.
Hunger is
still means death.
Food is a more essential resource that we need. But if you take a patient, let's say if a patient comes to a clinic and you have some disease, right, then you can lay on the bed and you can inject him with whatever drug. Let's say if you have something in the field, like you cannot go each plant and inject him and ask him how he's feeling. So there's a lot of challenges also there, and in a way the formulations need to be much cheaper, being able to produce it on a much larger scale. And at the same time, in a way, it has to be do some more advanced things in terms of
the actual chemistry. Yes. Amazing. Many of us try to buy organic produce to avoid pesticide residues. Could your technology eventually lead to safer fruits and vegetables with less chemical residue? And how might your research help create more environmentally friendly agriculture treatments?
So I think that if we'll allow to decrease the amount of pesticide that are being used in the field, and we'll achieve some of it. Mm-hmm. I would say that I also sometimes, like to buy some organic food, but I also think that as humanity and as scientists, we have to remember that if you go to purely organic, then probably not have enough food to feed everybody. Yeah. And this have consequences that we usually don't like to think about them when,
Right. It's very discriminatory.
Yes.
Yeah.
And so I think the way to go would be to find, again, the ways to decrease the load of pesticide on the environment, make them more specific, allow to use less and achieve more, and this would be the right way.
Nice. From lab discovery to pharmacy shelf can take years, if not decades, for medicine. Is the timeline shorter for agricultural applications, and what might farmers see first in your research? So
I would say yes, even though, again, I don't have a real product that went into the market on either field yet. Mm-hmm. I did have some collaboration with a small startup here in Israel. It's called Tom Grow. They basically developed hydrogel as a replacement for soil, so you can have a plant in your. Right now, is for indoors, so in your office, that you don't have to water very frequently, so you can water them every few months.
Oh, wow.
And this is a product that, came unready to our lab. We worked together with them. Yeah. And it's now being sold. So on this, I would say yes. So for something, you can see a very quick turnout of the technology that we were involved, again, with the startup.
And is that plant, could it bear fruit, or is it just
Yes, that's the point.
Amazing. We're, as a society, collectively experiencing how bacteria develop resistance to antibiotics. Similarly, pests develop resistance to pesticides. How might your approach help address this specific challenge?
So in some cases, you can think on, let's say, if the carrier, for example, would be activated by the same enzymes that are responsible for this drug resistance. So you can serve kind of a bit like a Trojan horse. Okay, and then you'll have to put a different drug that would act for a different mechanism to allow to bypass this type of drug.
So you would have to change it a lot.
You'll have to change. Yes, you have to change and fit it. Again, eventually nature is designed
to adapt
and evolve, and we are part of nature, so we have to play the game.
It's true. I'm curious about the testing process. How do you go from a promising idea in the lab to knowing it will work safely in the human body or on a crop? Looking at both fields, kind of in medicine and agriculture, what do you see as the biggest obstacle in translating promising laboratory results into real-world applications?
So I think you hit a very important point. Again, this transition from an idea that you have to later pitch to your students and convince them that this would be a life-changing idea.
This is the best idea ever.
Yes, and to leave whatever they were doing and go and do it. Mm-hmm. I would say in the field of nanomedicine, then the testing is something that is definitely very important. So for many years, people have tested drugs on a 2D, so two-dimensional cell cultures. And we know, again, it's known for many years, but the technology wasn't ready. Cells behave very different when they are on a 2D, so flat cells, or when they're in a three-dimensional structure. Mm-hmm. There's more and more work. We don't do it ourselves, but through collaborations, we have collaborators that create these three-dimensional models of tumors and healthy tissues, and we try to test them into these more realistic conditions. I think this is something that is essential.
Right.
So developing more realistic testing models, because otherwise, again, you could push something very far away and then discover that it's not working the way it should work. For plants, so creating these models, and then you probably still have to go through mice and different types of animals. Mm-hmm. On plants, I say in a way it's easier, right? We can grow the plant and test them.
Right.
I can tell that in one of our first experiments with this startup, we kind of killed 5 plants of tomatoes because we did something wrong with the chemistry. And my researcher working on this was she said, "Did you see the results? We killed all the plants." I go like, "Sit down, it's tomatoes. You know how many tomatoes I've killed in my life? Like, we're fine. If this would be mice or rabbits or right. Other animals, then I would be devastated. Yeah. But for tomatoes, like I can live with it."
Yeah. Out of curiosity, are you guys using any AI to help these models or any of the technology that you're using?
We're actually starting to implement this and pushing for this more and more now. Mm-hmm. One of the challenges is to find the right descriptors of the chemistry we do to put it into the AI machine learning.
Yeah.
But it's I definitely think it's the future. Mm-hmm. And it's already happening. So I am looking for collaboration in this area, and I think we'll see more and more of this.
Amazing. I feel like in our lives, we often hear negative things in the news about chemicals, but your work shows chemistry's positive potential. What's one misconception about chemistry you wish more people understood?
That's an excellent question. I think the biggest one is that people forget that chemistry is everywhere. Mm-hmm. So, right, we were talking before about growing something through an organic type of farming. Eventually, right, even organic farmers, they use different materials that maybe from biological sources, but they're still materials.
Right, there's still chemistry.
So chemistry is actually everywhere.
Yeah.
Okay, and I think this perception that some things are chemical that are bad, like it's for me as a scientist, it's very weird because everything is
right.
Everything is made from molecules and materials. So, so there's no bad or
good.
Yes.
And lastly, looking ahead to the future, what everyday experience with medicine or agriculture might look completely different in 20 years because of research like yours?
So hopefully in medicine, we'll see different types of diseases at least becoming chronic and not life-threatening. Hopefully being solved.
Right.
And I think that there is also an area where AI can really affect our life and allowing us to maybe predict better kind of what the risk of someone getting a specific disease.
Right,
and
like
then
preventative.
Yes, and going into preventive type of medicine. And I would say probably also for agriculture, it's like if you could use a combination of AI and more advanced delivery techniques to deliver the right material for protecting the plant or enhancing its ability to provide us with fruits and combining kind of optimizing the conditions and the delivery of a specific material at a certain time. This would be kind of So optimization of how we see, and we might see, plants growing, indoor and feeding us, from.
Amazing. Well, on this positive note, thank you so much for this conversation. It was very interesting.
Thank you very much, Gili.
And good luck with all the research. I can't wait to see what you do in the decades ahead.
Thank you very much. Same here.
תל אביב 360, ערוץ הפודקאסטים של אוניברסיטת תל אביב.